differential strain or the hoop strain. And typically, since the resistance is a very strong function of temperature, to take care of any temperature change that may be happening during the pressure measurement, we have a dummy strain gauge which takes care of temperature fluctuation. We talked about the construction of a typical strain gauge. You have a backing material which is made out of some kind of polymer. And on the polymer, you have the metal foil, which is patterned in a serpentine structure to ensure that the length is very high, so that for a given strain, the change in resistance will be very high. So typically, you mount the strain gauge onto the structure where you want to measure the strain, such that the strain direction should be aligned along the foil length. Okay, so the strain should be in this direction, not in this direction. If you apply strain in this direction, then just the structure will open up, and this foil will not experience the right kind of strain that can change the resistance significantly. So you have to ensure that the strain direction is along the length of these limbs. And as I said, typically this strain gauge forms one of the resistances in a typical Wheatstone bridge circuit. So you have an arrangement, something like this. So I will come back to this a little later. But before that, let us talk about how we can characterize a strain gauge. We typically characterize strain gauge in terms of what is called gauge factor. So for a strain gauge element, the resistance is function of its size. And for any kind of resistor, we write resistance R is basically rho L over A, where rho is resistivity, L is the length of the conductor, and A is the area of cross section. Now from here, if you take elemental resistance change, so you can write dr over R will be equal to d rho over rho plus dl over L minus dA over A. So basically, you take derivative of R with respect to each one of these parameters. And when you club them, you get dr over R as a function of rho, L, and A as so. Now, if the temperature is not changing, temperature is constant, the resistivity change would be 0. It's because resistivity is only a function of temperature. So at a constant temperature, assuming a constant temperature, you can write that the change in resistance over the original resistance will be change in length over original length minus change in the area of cross section over initial area of cross section of the strain gauge. But if you assume the strain gauge foil that you see here to be of circular cross section, then you can write that area will be simply pi into R squared. So dA over dr would be basically 2 into pi into R, so which can be written as 2 into area over R. And so basically dA over A will be equal to 2 into dr over R. So now if you bring in the definition of Poisson's ratio. Poisson's ratio is the ratio of lateral strain to the longitudinal strain. So basically, Poisson's ratio nu is dr over r divided by dl over L with a minus sign. Why there is a minus sign? Because if you take a wire, if the longitudinal strain is positive, the lateral strain will be negative. If the length increases, the area of cross section will reduce. So that is why you have a negative sign here. So as I said, the Poisson's ratio nu will be dr over r divided by dl over L with a negative sign. So dr over r will be equal to minus into 2 is there here, minus nu into dl over L. So this now we substitute here, dA over A, we substitute here. When we do, we get dr over r will be equal to 1 plus 2 nu into dl over L. And this is equal to 1 plus 2 nu into dl over L is basically longitudinal strain. That means when you mount your strain gauge, then now the strain is acting in this direction because of the pressure, internal pressure. The hoof strain will be acting in this direction. So each of these limb, the metal foil limb, will get extended. Okay, dl over L will be acting in this direction. So knowing the longitudinal strain and the Poisson's ratio, you can find dr over r. Okay, so you define something called gauge factor. What is gauge factor? Gauge factor is the ratio of the fractional resistance change, that is dr, to the original resistance divided by the longitudinal strain. That means dr over r divided by dl over L, and that gives you 1 plus 2 nu. Okay, so the gauge factor of a strain gauge, which is characteristic of a strain gauge, is simply 1 plus 2 nu. Now, Poisson's ratio for various materials are listed here. So steel is having a Poisson's ratio of 0.3, gold is 0.42, glass is having a value 0.2 to 0.25, elastomers are very close to 0.5. So we see that the Poisson's ratio are close to 0.5. So if you substitute here 0.5, it becomes 2. So that means for most of the materials, your Poisson's ratio would be lying between 1 to 2. Okay, close to 2, depending on the material. You can expect the gauge factor to be 2. Now, you use the strain gauges in a Wheatstone bridge as the fourth branch of fourth register in the Wheatstone bridge circuit. So typically, let's say your R1, R2, and R4 are standard registers, and this R3 can be the strain gauge that we are talking about. So typically, these Wheatstone bridge connections will be made with using lead wires to these two terminals. Okay, that you can see here. So if you analyze using Kirchhoff's law, you can relate the output voltage to the input or supply voltage. So typically for a Wheatstone bridge circuit, input voltage times a function of resistances. R1, R3 minus R2, R4 divided by R1 plus R4 into R2 plus R3. Now here, as I said, this R3 is the strain gauge element. Okay, and the other registers R1, R2, R4 are standard registers. And this arrangement is called the quarter bridge circuit. Okay. So if you take all the strain gauges are equal, and none of these registers are initially strained, that means you say that initially R1 equal to R2 equal to R3 equal to R4 equal to some R. So when that is the case, for a given supply voltage, the output voltage will be 0. That means the circuit is balanced. Now, when this R3 is mounted to some structure like this and there is strain acting on it, that means the resistance would change, right? From R3, it will become maybe some R3 plus delta R3. Okay. When it is strained. So in that condition, we have to know what is the kind of strain that is measured by the strain gauge. Okay. So first we look at the numerator of this term. So R1 into R3 minus R2 into R4. Now when there is the strain gauge here is strained, so it becomes R1 plus R3 plus delta R3 minus R2 R4. Now if all the resistance are equal, so you can write R into R plus delta R minus R square, which will be equal to R into delta R. Because R square and R square will get cancelled, it will be R into delta. Similarly, if you look at the denominator, R1 plus, this would be R1 plus R4, R2 plus R3. So this will be basically R plus R, and this will be R plus delta. Okay. So this would be basically 2R plus delta R, and this will be 2R. Now this change in resistance is negligible compared to 2 times R. So you can neglect this. When you neglect this, R plus R 2R, and this is R plus R 2R, so it becomes 4R square. Okay. So now in this equation, if you put in this numerator and denominator, you see that the output voltage will be input voltage into R delta R divided by 4R square, which will be equal to Vs into delta R over 4R. Okay, because this R and this R will get cancelled and it will be 4R. So output voltage is basically Vs into gauge factor divided by 4 into strain. As we had seen here, the dr over r is gauge factor into the longitudinal strain. So in place of dr over r, if you substitute for gauge factor into strain, it becomes Vs into gauge factor divided by 4 into strain. So now the strain can be found out as 4 into output voltage divided by the supply voltage into 1 over gauge factor. So in a given experiment, depending on the output voltage that you measure when this strain gauge is strained, from the output voltage, everything else you know, because supply voltage you are giving, gauge factor of the strain gauge you would know. So just by measuring the output voltage, you can find out the strain. And if you know the strain, you can know the pressure, because for a tube, the strain and the pressure are related using the stress formula, as we had shown it in the previous class. So that is how strain gauges are used for measuring pressure inside a tube or a container or anything. We talked about bellows and the bottom tubes and so on, where when there is a pressure change, there is a deformation of these elastic structures. And the question was how we can sort of measure these elastic deformations. And typically, in case of a bellow, for example, the deformation will cause linear displacement. And question is, how can we measure this linear displacement when this bellow is deformed? So one approach to measure linear displacement is using what is called linear variable differential transformer. Okay. So this is the typical arrangement. This is the pressure to the source that you want to measure, and this is connected to the bellow. And when the pressure changes, pressure increases, the bellow would expand. Now here you have an interesting arrangement. You have a primary coil and you have two secondary coils. Okay. And this bellow is connected to a core. And when bellow deforms, the core moves. Okay. So initially, you have the core located in an equilibrium position, and such that the output of the secondary coil 1 and the secondary coil 2 negate each other and you get a zero output voltage. So this is basically the electromagnetic principle that when you have a current carrying conductor, so this is a primary coil which is a current carrying conductor. A current carrying conductor will always induce a magnetic field. So that means you have a magnetic field here because this is a current carrying conductor. Now when this metal core moves through the magnetic field, it cuts the magnetic field lines, and cutting of the magnetic field lines will induce current in a secondary coil that are located here. So initially the coils are arranged tail to tail and head to head, so that whatever current is induced here and here are equal. Basically the net voltage here will be zero. Now when the bellow deforms, the core moves. Now the voltages induced in the secondary coil 1 and 2 will not be the same. It will be asymmetric. It will not be symmetric. So this asymmetricity will create a non-zero voltage here at the output. That non-zero voltage is related to the linear displacement of the core, which in turn is related to the pressure. Okay. So that is how LVDT can be used together with bellows to measure pressure. So that was based on linear variable differential transformer. This is another technique to measure pressure when you have a diaphragm. So we looked at the membrane mechanics to know that pressure acting on a diaphragm and the displacement of the diaphragm are theoretically related. So if you can measure the displacement accurately, you can predict the pressure accurately. Now the question is, how do we measure the displacement? So one approach is the capacitance type diaphragm gauge. So here you have this kind of arrangement. So this is the diaphragm. Okay, this diaphragm on the left side is exposed to the source pressure that you want to measure. Now, this is an anvil. Okay, so this is like a metal plate. Now, between the diaphragm, which is exposed to source pressure, and the anvil, which is like provide a metal surface, there is a gap. Now, when the source pressure would increase, this diaphragm will deform and the gap will reduce. Now, how do we measure the reduction in the gap? So you use the parallel plate capacitor principle. We know that for a parallel plate capacitor, having a plate area A and the gap between the plate is X, and the gap here is filled with a medium of dielectric constant K, then capacitance will be 0.0885 into the dielectric constant into the surface area of the plate divided by the gap between the plates. This is known. Okay. Now, if you say what is the change in the capacitance for a given change in the displacement, dC over dx, dou C over dou x, if you take derivative of this, it will be minus 0.0885 K A over x square. And that is simply minus of C divided by x. That means if you have initially designed a variable, a capacitance type pressure gauge, that means you know what is the capacitance here because you know the dielectric constant of the medium, you know the area of the plate, and you know the gap between the plate. Then you know the sensitivity. That means for a given change in the distance, how much will be the change in the capacitance. So typically this is, one can manually do it. But if you know the capacitance, then you can predict the displacement. And if you can predict the displacement, you can predict the pressure. So how do you measure the change in the capacitance when there is a change in the distance? That is done by this capacitance pressure transducer circuit. So here is the diaphragm. On the bottom side of the diaphragm, you have a chamber, and this chamber is connected to the source pressure that you want to measure. On the top side, you have reference pressure, which could be atmospheric pressure. Now, initially, the source pressure and the reference pressure are equal. Now, if the source pressure increases, now the diaphragm would deform. Okay. So before the pressure is increased, when it is equal to the reference pressure or the atmospheric pressure on both sides, the output is made to be zero because here there is a variable capacitor, and you just because the capacitance on both sides are going to be equal, you see that the output, the current will be zero and the output will be zero. Now, when this chamber is connected to source pressure and the diaphragm deforms, the capacitance on the top side and bottom side will be different. So here, the capacitance here and the capacitance here will be different. Now, this is a variable capacitor. So when these two capacitors, there will be a non-zero current. Now, you try to adjust this current, adjust this capacitance until the current becomes zero. And when the current becomes zero, because of the adjustment of the capacitance, there will be a non-zero output. And it is this output that is related to the pressure here. Okay. So that is the principle of a capacitance type transducer. Okay. Now, we have talked about various pressure transducer. We talked about initially we talked about manometer. So manometers can measure,
Sir, one question I have, can I ask?
Yeah.
If we go to the previous slide.
Yeah.
So basically, you have told that the arrow marked capacitor is the variable capacitor,
Yes.
and the upper one is a fixed one, known capacitor. So once the capacitance value of the variable capacitor is adjusted in such a way that the both capacitor becomes equal,
Yeah.
then there will be no current, right, sir?
Yeah, there will be no current, but there will be a non-zero output here.
Oh, why, sir? I could not gather it. Like
See,
the mechanism behind that.
because see, when this deforms, basically the amount of charge that will be stored here and here will be different. Okay.
Okay.
So now by varying the capacitor, you are basically equalizing the current. But since the capacitance now is different on these two circuits, if you do a circuit analysis, you will see that it will result in a non-zero output.
Oh, yeah. Basically Q1 upon C minus Q2 upon C, right? That.
Yeah.
Right, sir?
Yes.
Okay. Fine.
Okay.
Fine.
So we talked about manometer, which can measure pressure slightly subatmospheric to about 10 to the power 4 millimeter of Hg. Then we talked about McLeod gauge, and this will be basically this can measure subatmospheric pressure, where you remember, we are able to trap the gas which is at below atmosphere and compress it using a liquid, and using the Boyle's law we are able to predict the pressure. So that is the McLeod case. It will give you the subatmospheric pressure measurement. Manometers are slightly below atmospheric to mostly above atmospheric pressure. All these other elastic-based pressure transducers can only measure above atmospheric pressure, bellows, diaphragm, bottom gauge. And then the strain gauges, you need considerable amount of pressure and which can create significant strain that can be read. So this electric resistance type is basically the strain gauge based pressure measurement, so which is at a relatively higher pressure. But if you look at here, you can you have only McLeod gauge for measuring vacuum pressure. And the McLeod gauge is not really suitable for measuring pressures which are frequently changing. And they have the limitation that when you compress, subatmospheric pressure fluid, you may have condensation problem and so on. And this is manually done. So alternative to this for vacuum pressure measurement are ionization and Pirani gauges. So we are going to look at these subatmospheric pressure measurement gauges, which are typically commercially available, but we can look at what are what is the principle based on which they work.
So, Professor, just one query over here.
Yes.
Like you told that bellows and diaphragm and Borden type and these things are not suitable for measuring the vacuum pressure.
Yes.
But the principle behind this is that when there is a relative pressure in the system, the bellows will expand or maybe displace or whatever will happen, and hence by measuring the voltage difference and all, we can know what is the pressure level.
Yeah.
So if there is a positive pressure, definitely the bellow will expand and diaphragm will expand, or this thing will happen.
Yeah. So,
but suppose if we apply the negative pressure over here,
yeah,
then the bellow should contract and it should measure the
yeah,
negative pressure as
bellow.
well.
I mean, you should know really the construction of bellows. So these are basically, how it looks when the pressures are atmospheric. Okay. So
Closely packed.
there is no room for compression. They cannot take, compressive load as such. Okay. So they would only expand.
Okay, sir. What if there is a gap between these two coils in that way?
Well, I mean, that is how they are fabricated. Okay, so you can look at some practical pictures of bellows. So they are not really suitable for taking compressive load.
Okay, sir. Thank you.
Okay. So what is the principle behind the thermal conductivity gauges. The principle is that, so these are basically thermal conductivity gauges. First, we are going to look at. The principle is that at low pressure, thermal conductivity of gas varies with pressure. Okay. This is not really the case when the pressure is above atmospheric, but when the pressure is vacuum pressure, the thermal conductivity of the gas is a strong function of pressure. So, as we will see subsequently in the construction, that typically these gauges will have a filament which is heated by passing electrical current through them. And they are placed in a container filled with the gas whose pressure we want to measure. And you would see that when you are passing current through the filament and you have this in a container filled with gas, there is going to be I square RT heating, the resistive heating. When resistive heating happens, the temperature of the wire would depend on the current because the resistance is fixed, so it will depend on current. Also, it would depend on the rate at which heat leaves the filament surface. Now, if you keep the current fixed, if you keep the current fixed, then the heat loss would depend on the thermal conductivity of the medium. And the thermal conductivity of medium depends on the pressure. That means essentially, when the current is kept constant, the temperature of the filament, or consequently the resistance of the filament, because the resistance and temperature are related, would change with the pressure inside the container. So that is the principle. Okay, so first let us look at the Pirani type thermal conductivity gauge. So here, the change in resistance of the heated wire is measured using Wheatstone bridge. So you can see here, this is the wire that we are talking about. And this wire is inside a container, which is the measuring cell. And this cell is connected to the source pressure. And then you have, this is in one branch of the Wheatstone bridge. The other side is another resistance. Then you have these two resistances. So the four resistance form the quarter bridge circuit, Wheatstone bridge circuit. And the second coil is for temperature compensation. Any ambient temperature fluctuation it will address, because whatever fluctuation this will see, this will also see, so they will nullify each other. Now, you are supplying some voltage, so there is some current going, so that is resistive heating. Now, the temperature of this wire or the resistance of this wire would depend on how much heat is leaving the filament to the gas, because that would depend on the conductivity of the gas, which in turn depends on the pressure of the gas. Okay. So initially, when everything is at atmospheric, your Wheatstone bridge is balanced and there is zero output. And when you expose this to the vacuum pressure that you want to measure, then you see that depending on the pressure of the gas, the resistance would change. And when the resistance changes, you are going to see a non-zero output voltage here, which is calibrated against the vacuum pressure. Okay. And typically, these Pirani type thermal conductive gauges are used for measuring pressure about minus 10 to the power minus 5 torr to about 1 torr. So these are mainly vacuum pressure, low, very low vacuum pressure measurement can be done. instead of making an indirect measurement of temperature, one can directly measure temperature of this using a thermocouple. Okay, so that is known as thermocouple type gas. That means you say that when I do when I pass current through it, how much will be the temperature of this heated filament? I can measure directly. Okay, and the temperature of the measured filament will depend on how much heat loss that happens, which in turn depends on the thermal conductivity of the medium, and which depends on the pressure. So instead of measuring the resistance, you can directly measure temperature using a thermocouple. Okay, so that is just an alternative to the Pirani gas. This is known as thermocouple type gas. And again, I mean, the pressure range is about 10⁻⁴ to 1 torr. Then we have ion. So the ionization gas, the principle is that when you have an ion passing through a medium, the number of molecules it will ionize would depend on the number density of molecules. And as you know, for a given volume, higher is the pressure, higher is the number of molecules. And hence, number of molecules that will be ionized is related to the pressure inside. Okay. So here you have this arrangement. You have a source voltage here, and this is the cathode. And at high voltage, electrons are emitted from this cathode. And they are accelerated. And when these electrons strike the gas molecules they will basically knock off the electrons, leaving only the positive ions. The positive ions will accelerate towards this negatively charged plate and give rise to some current, which is I subscript I in this circuit. The ionized electrons, the knocked off electrons, will be connected by this positively charged grid and give rise to this current, which is I subscript E. Okay. Now, one can measure the pressure of the gas using this formula, which is 1 over the gas sensitivity into I subscript I divided by I subscript E. This is the current that is because of the positively charged ions. This is the current because of the knocked off electrons. Okay. And we can see that if there are a lot of molecules here, then your II will be higher than IE. That means you say that the pressure is relatively higher. But if there are only few molecules, because it is vacuum, I mean, it is not absolute vacuum, it is just subatmospheric pressure. Nevertheless, there are some molecules. So if there are very less number of molecules, that means your II will be small and your pressure is going to be small. So that is the principle behind the ionization gauge, and typically ionization gauge is used for measuring ultra low pressure. So you can compare this with the Pirani gauge, which starts at 10⁻⁵ torr, but ionization gauge can go up to something like 10⁻⁻10 to 10⁻⁻2 torr. Apart from that, you have alphatron gauge. This is another vacuum gauge. And here, unlike the ionization gas, here in alpha-trin gas, the ionization is done by the alpha particles, which are released by a radioactive source. Okay, as you know, radioactive materials, they do emit alpha particles. And these alpha particles, when collide with the medium that is present here, would ionize them. And these ions then would be collected using this collector electrode that you see here. And these ions, when they are flowing through this circuit, would give rise to proportionally an output voltage. Okay? And this output voltage will then be related to how many ions are going to land in the circuit, which is again related to the pressure of this medium. The range of pressure that you can measure is typically between 10 to the power minus 3 to about 10 to the power 3 torr. So apart from this, the recent advancements have led to small pressure sensor, which are called MEMS pressure sensor or micro electromechanical systems based pressure sensor. Basically, this has come from the fact that we are able to shrink down, circuits motivated by the developments in the integrated circuit industry. So I'm going to talk about few. There are several advantages of pressure sensors because all these pressure transducers that we have talked about are, large scale systems. Okay, so their physical size is very large. So if you want to develop a system where physical size is a constraint, and you want to create a very, very small pressure sensor of few millimeter by few millimeter size, then you need to talk about MEMS pressure sensor. Okay, so there are several advantages in terms of the high volume production because it can really leverage the processes that are followed in IC industry. Then there are several advantages in terms of the size, weight, and so on, and how you can integrate with different kinds of other sensors or small devices that you need for certain systems. So typically, the principles are similar, just that the structures are very different. Okay, you can see that they are typically, less than a centimeter to even close to a millimeter. Okay, the sizes are really, really small. Okay, and the principles are similar. Like you will have a diaphragm, for example, and you have an applied pressure that you want to measure. So that this pressure will deform the diaphragm. Now, the deformation of the diaphragm is measured using the sensor, either by looking at the changes in the capacitance or changes in the resistance. So typically, you will have this kind of structures made out of silicon. As I said, this is motivated by the IC industry. So the starting material is always silicon. So you basically etch silicon to create this kind of trapezoidal grooves. And you create, so that means you basically have a thin film of silicon, which acts like a diaphragm that you see here. And silicon is a semiconductor. So if you want to know when this film deforms, the resistance change across or the capacitance change across, you have to make electrical connection. So you basically create these electrode connection points indicated by these black rectangles through typically boron implantation. And so you can make a connection to the external circuit through these points. And when there is so if this is the bottom side is exposed to the source pressure, the pressure is high, this is going to deform, and the deformation is going to change the resistance between these 2 points. Or if there is another electrode here, then the capacitance would change, right? So these are different designs that you see, just they are, structured differently, and the manufacturing process that can be used is different, but the principle is the same. Either it is capacitive or resistive. So this is where we looked at the resistance change, and you can also have capacitance change measurement. As I was saying, that you can have a filament here, the diaphragm here, and the bottom end of the diaphragm has one electrode, and the bottom side of this chamber has another electrode. Now, when you have a pressure difference across the diaphragm, when there is a deformation, the capacitance between these 2 electrodes would change. And depending on the capacitance change, you can predict the gap. And knowing the gap, you can theoretically predict what is the pressure. So this works similar to, macro scale, large scale pressure transducer. It's just that their sizes are very small. You can really integrate them into very, very small systems and devices in there. So again, the cross sections can be varied. For example, if you can use a structure something like this, where the deformation profile will be parabolic, because the mechanics says that the maximum deformation will be at the center. You can even create special designs so that you will have a different flexural rigidity at different point between the walls, so that this kind of structure, when it's exposed to pressure, will not give you a parabolic deformation profile, but instead a more of straight rectangular kind of deformation profile. So that is ideal for capacitive, capacitance measurement, because then the distance between the 2 plates will be same everywhere. Okay. Otherwise, there will be a variable capacitance across, right? So this kind of modifications also people have tried to implement. So I will stop here. If you have any question, we can discuss.
Sir, can you just repeat on the last part regarding that flexural
Recording
rigidity
stopped.
variation?
Okay, yeah. Sorry. So if you take if you go to the fundamental strength of material, right? So if you have a clamped beam and the cross-sectional area doesn't change, then if you apply an uniform pressure, the beam is going to deform into a shape like this, where the deformation will be maximum at the center and minimum at the walls, right? So one modification that people do to make this deformation profile more and more uniform, flatter profile, is by changing the flexural rigidity across the length of this beam. that you do by increasing the cross-sectional area at the middle and reducing the cross-sectional area at the sides. So you know that if you go to the strength of material basics, there is a term called E into A, that is your bulk modulus of elasticity into area of cross-section. So
Friction modulus.
you have E into I, you have moment of inertia.
So yeah, EI by L, right?
Yeah, EI by L. So you have EI by L. So the I, you can actually change by varying the cross-sectional area. Okay. So this is a nice way of, so that your profile is now becomes flatter. So in this particular case, now if this diaphragm deforms, now the gap between the plate will be uniform everywhere. Okay, it is not going to be smaller at the middle and higher at the edges. It is going to be more or less uniform. So people adopt this kind of modifications in.
But the size is very small for this sensor, right? So how do they locally do all this?
No, anyway, see, I mean, the size that you are saying is small is big for people who do IC manufacturing, right? So, I mean, typically they do that in, okay, this is something that I have to teach you, but there's a process called photolithography, oxidation, diffusion, etching. So these processes they follow to create this kind of structure. Okay,
Got
so
it,
it's
sir,
not really, milling or traditional machining. They do what is called clean room processing. Okay, that people in semiconductor manufacturing adopt.
Thank you, sir. Yeah.
So it is basically an both an additive and subtractive manufacturing process. You add material and selectively subtract material through etching. So you deposit material, you etch material selectively, and you pattern them using various ways. One of the ways is called photolithography. That means you use light to actually define patterns and create this kind of structures.
Sir, one request, whether we'll get this slide, sir, basically, so that we
Yes,
can
yes,
again...
I have to give you, I think, I will share, I think I got an email regarding the questions.
Right.
Sure. And I would
Right,
say,
sir, right.
I would share everything. I have been forgetting, but I would do that.
Okay.
Okay. I would share
the concepts are
question.
very critical, actually. It's like very tricky concepts are there in the subject. Very interesting.
Yeah, please read through the books. As I said, this SP Venkatesan book will nicely cover these aspects that we are talking about.
Thank you, sir. Thank you so much.
Thank you, sir.
So thank you, and I do not think we are going to have class tomorrow.
Okay.
So in that case, if we have it, then I will send you an email. But if you do not get an email, that means we won't have class tomorrow. Okay.
Sir, one more information, sir.
Yeah.
So we discussed in the earlier starting of the class session, sir. We requested to prepone the exam end semester to 1 week before 1 week. So finally, they said it is not possible.
Yeah, I got those email communications, but I mean, I do not know how I can help you with that.
Sir, because we are all are working people, so very difficult to write the exam one after another. That is what we requested.
I understand, but okay, so this is kind of slightly different than what we do at IIT. I mean, there is some more flexibility, but I do not know the limitations that that code office has for not agreeing to your proposal.
Okay, no problem.
You understand my,
Understood, sir. Understood. Understood.
even if I want, I cannot help you here.
Okay. Right, sir. Right, sir. Thanks, sir. Thanks for that.
Thank you very much. Thank you all.
Yeah, thank you, sir.
Thank you so much, sir. Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you, sir.